when we were writing TinyML earlier, we had to handle all these annoying cases where you're, for example, adding two things, but the values you get from the recursive evaluation call aren't numbers. This is something that never happens in real ML languages because the type system prevents that. So let's have a look at how type inference in ML-like languages works and how it prevents these kinds of things from happening. So I'm going to talk about type inference in this lecture, and this is not a programming system. So we're going to be extending the TinyML, sort of building on top of a similar structure. And the interesting aspect here is that the type inference and the way types work in ML is an important part of the ML experience. So if you think about how you interact with an ML-like language, one important aspect of that is that you don't write the types, you write code, and the compiler behind the scenes infers the types for you. And as we will see soon in F#, this is something that's integrated in the editor. So the editor will tell you these are the types of the things that you've written. And I think this is a really sort of important part of how the programming system works, because the way you typically write code is that you will write a little bit of code, check that the inferred type is what you expected, and then continue coding. So in this sense, it's sort of a part of the typical ML-like programming system experience. As we look at this, I will also point out some interesting subtle aspects of F# or ML type inference. Interestingly, some of those were things that people did not initially realize when they were implementing the first ML languages. So there were some interesting issues arising from some of the design decisions. And we will look at those, and through your own implementation of the type inference, you will see where the subtle cases are. And finally, type inference is based on constraint solving, and this is a technique that we will also need in the next course looking at Prolog. So this is sort of introduction to a very general purpose useful technique. ML as a programming language has its origins in a thing called LCF, and this was a theorem prover built in Edinburgh in the 1970s. And initially, that was sort of a tool for checking proofs using a computer. And one of the things that they needed in the prover is some mechanism for sort of generating proofs. So ML was created as a meta language, hence the name, for writing code that generates proofs. So you would sort of get bits of a proof and compose them together by invoking some functions on them. And in this context, the type system was used to guarantee that you are only able to construct valid proofs. So the types were there to ensure that you own all the things that you can create in the language are valid proofs. But later on, ML sort of turned out to be useful as a standalone programming language, and it evolved in further directions. But the type inference is something that was there in the sort of early days of ML. So type inference, the algorithm that is behind what ML initially did, and that kind of remains one of the interesting algorithms in many subsequent languages, was actually invented earlier than ML. It appeared in 1969, and it was created for sort of logic, for combinatory logic, in the context of sort of thinking about proofs. And later on, when Robin Milner created ML in the 70s, he independently invented basically the same algorithm for the ML language. And the sort of key idea there was that you can sort of infer that the types but it doesn't just doesn't just sort of check the types of primitive expressions. It also has this ability to generate polymorphic types, which is something that we will soon see. And so those were sort of the two independent inventions of the algorithm. And later on, the algorithm is sometimes called Hindley-Milner-Damas, because Damas was a person who looked at it and sort of done the formal analysis and proved that this actually terminates, and so on. So since then, people have been kind of using type inference or extending type inference and type systems with plenty of other language features like type classes and other extensions. And there's often a question whether you can still infer the types fully automatically without any annotations in the sort of ML tradition, or whether you need some different way of interacting where maybe the users will actually have to write some types. Before looking at TinyML and type inference there, I want to get back to one example that I was showing earlier, which is the coeffects project that I did for my PhD thesis, where you can see a sort of one interesting extension of the type inference algorithm. So the example that I've got here is I have a language where, in addition to writing using normal variables, I can use these question mark identifiers. And they represent something called implicit parameters. And the interesting thing here is that the implicit parameters can be defined sort of later on when you're calling the function. So I have this example where I'm saying add, and the function takes an x, and then let's make this a little simpler. So I'm going to say x plus some implicit parameter called fst. And then later on, I am going to set fst to 40 and call the function with, let's say, 2 as the argument. Now, if I do this, then I have satisfied this requirement because I provide the value in the call side when I'm calling the function. If this was taking some other implicit argument, say snd, then, and I evaluate it, then this is now a code that still requires the value of snd, and in this web interface, I can put some value here, and it will then run the computation. So in addition to checking that x is an int, what this is doing is that it's also checking that this function is a function that takes some implicit arguments. When I call it, I have to have those values available. And how does this work? So there's a system at the end where I can take my code I've written, paste it in here, and it will type check the code for me. So if I check it, then I'm going to make this a little bit more interesting, because the values for these implicit parameters, they can come from both the declaration side of the function and a call side of the function. So if I actually say add is a function which I construct by sort of locally defining the implicit parameter third, then I'm going to create the function that takes x, requires first and second and third. Then I'm going to set first to 40 and call the function with 2 as an argument. Now, if I check this, then the system infers that add is a function that takes a number, returns a number, but it requires fst and snd. And we can sort of click through the typing derivation here and see that in here where we're defining the function, if I sort of click all the way inside, the body of the function, so that's here, this is something that requires, uses the variable x. So here we have x as a number, and then in this green bit, it sort of says, I also need these 3 implicit parameters. But when I look at the function definition itself, that's here, the system sort of sees that third is already available. It's sort of defined in the context where the function is defined. So the function that we get as a result will just require FST and SND. And so right here, I am defining third to be 1000. And then that means that this is available in scope where I'm defining the function. And then the function will just need the remaining arguments. The point of this is a sort of example of a system that takes ML-like language, adds an extra feature to it, but is still able to infer the types automatically for you. So I never have to explicitly define how this works. Where the arguments come from, that the system sort of infers. You can actually have a look at the source code for this. There's sort of, this is maybe interesting because you will see that the same pattern that we will be writing in our implementation, all the same patterns can actually appear in a sort of bigger, maybe more interesting languages. You can look through the code, but there's things like substitution, where we have to replace variables with values in types and in these extra annotations. There's some sort of function that solves constraints and so on. And so those are the exact thing that we will be writing later on. So the type inference algorithm that we want to write is basically the same as the type inference algorithm that exists in F#. So let's have a look at how this actually works in F#. I'm going to go through a couple of examples. So the basic thing I can do in F# is that I can say x is 42, and then part of this programming system experience is that I can have a look at the type, and it says x has been inferred to type int. If I say 0.0, then F# figures out this is a floating point number. If I write something like add xy, which will take x and y and add them, then interestingly, this infers the type int. So x and y are going to be integers because the sort of default type that's used for plus is an int. But if I, for example, edit 100.0, then the engine infers that this is a floating point number because I'm not really using just integers. So the addition and the numerical things, they're kind of a special trick in F#. But otherwise, you can see I'm sort of writing code and the types get inferred. Let's try something more interesting now. So I'm going to write a function called twice that takes a function as an argument, takes a value, and then applies this function to the argument, but then applies the function again on the result it gets. Now, this is an example of a polymorphic function because it can work with all sorts of different types. And if I look at the inferred types, the type inference is telling me the twice function takes an f as an argument. This is function from some a to some a. It takes a value x of type A and it returns a new value of type A. So it did figure out that the input and the output of the function f have to be the same because I'm sort of taking the output of f and passing it again to f as an input. If I didn't do this, if I just called f of x, Then the inferred type is more general. It just says A to B, takes A, returns B. Because then there's no constraints on that would force the input to be the same as the output. So how can we use this function? I can, for example, say this is going to be a string, and I'm going to take the string, add a comma, and then add it here again. And if I give it hello, then after I define my function and run it, it says hello, 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 hello. If I say twice and use a function that multiplies the number by 10, and I apply this to 4, then the result is 400. So this is an example of a sort of interesting case for the type inference because it infers that the type is general. And the clever thing that ML is doing is that it sort of uses these top-level let bindings and generalizes from the types that it infers there. So for your top-level functions in ML, you will get a polymorphic type if there is an option to do that. And this is something that's very useful when you're writing some more complicated functional code. So if I'm, for example, writing a function called map that takes a function and some sort of list, this is going to be a recursive function, then this is just a normal list map function where we pattern match on the list and say if it's empty, the result is empty. If it's x followed by some x's, then we're going to call f on x and recursively map over the x's. And so now I can call map and maybe give it a function that takes a number and multiplies the number by 10. And I'm going to give it a list from 1 to 9. And now we get multiples of 10. The interesting thing here is that the type we get here is, again, polymorphic. We didn't have to write any generic types like in C#. We didn't have to say f is from type T1 to T2. This is all inferred. And we're going to have a look at how this actually works. So this was some basic examples. And what F# is doing behind the scenes is that as it sort of reads your code, it will collect constraints. It will generate constraints based on sort of what the types of things are. So in the twice function, for example, eventually it generated a constraint that the output type has to be the same as the input type. And then it figures out they're the same, and it will use this name A for the type. In ML, you didn't need any type annotations. In F#, there are some cases where you need them. And then the sort of other thing I was mentioning is that ML-like languages do let polymorphism. So when you have a let-bound function, the type inference will try to make those polymorphic and generalize the types. There's various other interesting cases in ML and F#. In F# specifically, when you deal with .NET objects, that comes with various restrictions. In ML, there's also an interesting feature called value restriction, which I will show because it's sort of an interesting aspect of how the type inference works. And it's also something that in the early days of ML, people often got wrong. So let's say we want to write a function to calculate the length of a list. And you can do this by calling the default function that exists in the standard F# library. This takes a state. So this takes a function that the default operation maintains some state. And it sort of updates the state for every element. And it takes this folder function that gets the current state. So that's my number of elements. Then it takes an element and I'm going to return new state. Now I don't care what the element is, so I just put underscore here. and then I need to give it initial state and my list. And so now I can call len1 and give it a list with 3 elements, or I can call len1 and give it hi there. So it works, it's a polymorphic function. Now, an interesting feature in F# is that you can use partial function application. So if I just say this, then the bit of code I have here is actually defining a function that takes a list. And if I call len2 on my 1, 2, 3, then this still works. I can run this and it gives me 3, but you might see here that when we defined len1, it was a list to int, whereas now it's an int list to int. And indeed, if I take the other input here, then this is not going to work. So what's happening here is that F# has and ML languages in general have a restriction which says if you're defining something that syntactically is a value and not a function, it's not going to be polymorphic. And so F# kind of reads all my code and says, okay, this is a function int that takes an int list because that's the first thing we're giving it, and I get an error here. Why is this the case? So the sort of interesting problem that earlier ML languages had is that you can create these reference cells. And a reference cell is something that's like a mutable storage, and you can sort of see here that I sort of can't just run this definition because it doesn't know what's the type of this value. And when I have a reference cell, I can write to it using this operator. So maybe I can say, I will store in some value, and then I'm going to read the value and look at this. And if there's something there, then I'm going to do n+1. Otherwise, I'll just return 0. So the definition here, that itself doesn't constrain the type in any way. It could be, stores an option type, but it could be an option type of anything. But because of the value restriction, the F# compiler will not let me define this as a polymorphic type. I cannot say this is some sort of option of anything because it's a value, and when I use it as a value, if it was polymorphic, I would be able to write this code that would store string into it and then read it as a number. If v was really of this generic type, then we would be able to put in string and read out a number. So that's the reason why value restriction exists. It prevents me from defining generic values or polymorphic values because in some cases that would actually lead to bugs. So I'm not able to do this. You can't treat value as a polymorphic. So that was one interesting limitation of ML itself. There's a few more interesting aspects that happen when you interoperate with .NET. So I have one example here, and what I've got here is a list of dates. So this is some date values, and when you have a date in .NET, you can do dot on the object, and we can access various things like let's say what is the number of ticks, underlying representation of the date. Now, if I wanted to get these ticks for all the elements in this list, I could say I want to do a map where I take the date, and then on this I will do .ticks, and I will give dates to my list. And F# does not type check this because when it's analyzing the code, by the time it gets to this point where we access the ticks property, it doesn't yet know what is DT. And so it cannot know that whether it will be able to access ticks on this or not. So in F# specifically, there's this sort of order dependence where as it's solving the constraints, if you can resolve a constraint before you use some object, then you will be able to access the properties. Now in F#, I could add a type annotation and say this is a date time, and then it's perfectly happy and I can transform all my lists. But there's another interesting trick, which is that if I use the pipeline operator and put dates on the left, then now the type inference actually is able to figure out that dt has to be a date time by the time it analyzes this bit of code, and then I'm able to access ticks. So this is another sort of nice reason for using the pipe operator in F# in practice. So now we've covered all the basic aspects of type inference, how it's used in F#, how it appears in ML. So we're going to look at the next step, which is how to actually implement this.